Okay. So we got a function f of x y equals x squared plus y squared. And I've asked everybody to make a table where x takes values 1, 2, 3, y takes values 1, 2, 3. And we easily get these values, 9 values. Okay. This table is going to correspond to values of the paraboloid. It's just an elliptical paraboloid. Okay. And a rectangle that goes from x equals 1/2 to x equals 3.5, and y equals 1/2 to y equals 3.5. Why did I choose 1/2 to 3.5? It's because the point 1, 1 lies in the middle of this rectangle. Okay. In other words, the values at the middle of each of the rectangles here correspond to the values we have up here. So you can say, okay, the values are 3, 9, 19, 6, 12, 22, 11, 17, 27. Now you can imagine the elliptical paraboloid coming out this way from the XY plane. So in the first quadrant, this quarter of the elliptical paraboloid would be 3 units high here, 27 units high here, 19 units high here, 11 units high here. It goes high faster in the Y direction than in the X direction because you have 2y squared. And the numbers you're squaring, if the numbers you're using for X and Y are identical. So what you have is like something reasonably close, although not all that close, to the average value of this function on each of these rectangles, right? Okay. So okay, I was careless. I had these numbers going the wrong way. The y values go 3, 9, 19 when x is 1, so that would be here, here, and here. So I had rows where I could check that column. Not going to make any difference for what we're calculating here, but nice to have it correct. Okay, so thank you. Okay, so now, again, these are reasonably close to average values on each of these rectangles. Okay, now before we're done, we're going to calculate the average value in every rectangle, in every square. But right now we want to get the average value on the entire 3x3 square. Okay, so what's the average value I'm just doing the product, cross product, if you like, it's not really cross product, but it's the set product of two intervals. The interval is from 1/2 to 3.5, 3.5 to 7.5. So it's this interval in the X direction, this interval in the Y direction. So this is just the square that I've drawn. Okay. So what's the average value? How would you get the average value on that rectangle? Okay, so it'd be 3 plus 6 plus 11. Plus 9 plus 12 plus 17 plus 19 plus 22 plus 27, all divided by 9. Okay, so what's that add up to? I'm going to add that up quickly, but I'll probably screw it up. That's 49, that's 67, that's 84, 96, 105, 116, 122, 125. Mark that, we did that quickly. 125 divided by 9 is going to be 5, 13 and 8/9. Now, does that make sense? All these numbers, there are 5 numbers here that are less than 14. That's approximately 14. And then 4 numbers that are greater than 14. The ones that are greater than 14 exceed 14 by a little more than the ones that are less, but that's reasonable. Okay. So let's just say that's it. And if it's not right, you get it? That's okay. It's okay. So it's easy to do that. Okay. Well, I'm just going to cut to an integral that we can get the actual average. Okay. So here's what the integral looks like. Then I'll explain a little bit about it. Okay. What does this say to do? What's the first thing? What's the first operation that you would do in order to do what I've written down? That's probably unfamiliar to you, but it's not hard to deconstruct what to do. What do you think we should start doing? Well, we've got the recording going, so I'm going to take that as a rhetorical question, but you've thought about it a little bit. I'm going to do what's in the dang parentheses. Okay. That's going to be the integral from 1/2 to 7/2 of. Okay, now how do I do the integral of x squared plus 2y squared with respect to y? I treat x as a constant and do the integral. So what I get is quantity x squared y plus 2/3 y cubed evaluated at 1/2 7/2, and then with respect to x. Now, do we see that? If we're treating x as a constant, then the integral of x squared with respect to y, well, the x squared kind of comes out of the integration. We just have an integral of dy, so we get a y. Okay? And then that's multiplied by the x squared. X squared is just a constant. Another way of seeing that is if I take the partial derivative of this thing with respect to y, don't I get this? What's the partial derivative of x squared y with respect to y? It's x squared. Partial derivative of y cubed with respect to y is 3y squared. 2/3 of that is 2y squared. So that's very, very simple. Okay. So yeah, we'll do a little more systematically, but it's not hard to get used to that. Okay. Now this is between the limits 1/2 and 7/2. You might want to say between y equals 1/2 and y equals 7/2, so you don't get confused about what to substitute for the numbers, right? If we do that, we get the integral from 1/2 7/2 of x squared, because we're going to substitute y equals 7/2 and y equals 1/2, we're gonna do what we get for y equals 7/2 minus what we get for y equals 1/2. And 7/2 minus 1/2 is just 3, so we're gonna get 3x squared here. I'm not doing all the details, I'm just giving you the kind of the overview. And as you work through examples, the integrals here are fairly simple if you remember how to do it, okay? Okay, now 2/3 of y cubed. Well, that's a little more complicated. 7/2 cubed is 343/8. And 1/2 cubed is 1/8. So you get 342/8. That's going to give you 684 over 24. And we've still got a dx on it. Now, I did that in my head. But 3.5 squared, 3.5 cubed, going to be around 40 something. And 1/2 cubed is going to be insignificant. Got like 48, that would be like 32, and multiply that by 3, yeah, comes out reasonable. So it's plausible, just checking it against a different way of estimating what it ought to be. And the numbers might be right, but my working memory is always suspicious, so. So anyhow. So now we integrate that with respect to x. Of course, we can reduce 684 over 24, but I probably screwed up, so I don't want to. That's going to give us x cubed over 3. 684 over 24 x evaluated between 1/2 7/2. That makes sense? Okay, well, x cubed is again, you're gonna cube 7/2 is gonna be again 343 over 8. You're gonna subtract that, you got 342 over 8, and you're gonna end up with 684 over, no, not 684, just 342 over 24. Okay, that's going to be 9. That's going to be 1,000. That better not be 1,024 because it's power, got a power of 7 in it. Like 1,026. That's approximately equal to 42. Plus or minus 1. You can work out the numbers, so, but, try to work those numbers out a little more carefully. Uh, okay, it's gonna be a little higher than that because I did some down there. X cubed over 3. No, it didn't. I mean, I'm sure I did, not what I thought I did. Okay, now, if I want to find the average value of this function on this rectangle, what do I do? I think you do get the average value, assuming the integral is 42. And hopefully I will return close to this, but I don't know. We start with the function f x y x squared plus b y squared. We calculated its values for x equals 1, 2, 3, y equals 1, 2, 3, put them in a table. Well, then we depicted a region of the xy plane from y equals 1/2 to y equals 3.5 or 7/2, and from x equals 1/2 to x equals 7/2. Okay, and we said that these numbers occurred at the points right in the center of these squares. In other words, this square goes from 1/2 to 1.5. So halfway between 1/2 and 1.5 is 1. And halfway between 1/2 here and 1.5 here is 1. So 1 is right at the center of this square. At the 0.11. And the 0.21 is at the center of this square, and the 0.23 is at the center of this square, and so forth. So these would be the values at the centers of the square. If we want to calculate the average value on this square, which could be indicated by this x interval, the Cartesian product of this interval with this interval, and this just represents square. We can add these numbers up, divide by 9. If I added them correctly, we get 13 8/9. And that's the average value of this function on this square as estimated by the midpoints of these small rectangles. Now, we did an integral. Okay, I just wrote down an integral and said that this integral should give us the actual integral of the function f x y over this square. Okay, y goes from 1/2 to 7/2. X goes from 1/2 to 7/2. So that's explanation of these limits. We'll do more with this in a minute. We integrate with respect to y first, which means that we just do this integral treating x as a constant. So the antiderivative of 2y squared would be 2/3 y cubed. In the antiderivative of x squared being a constant would just be x squared y. This integral then would give us this expression evaluated between y equals 1/2 and y equals 7/2. And that gives us this. Okay. Which we then integrate with respect to x, because this is our inner integral. We still have our outer integral with respect to x. So now we integrate this expression, getting antiderivative x cubed over 3 and plus 684 over 24 times x. Of course, that could be reduced to the way it is. And I think we get this something like 78. Then we correlate this with the actual average value of that x, y on the rectangle. And by the integral, that average value would be the integral divided by the area. Now that should make some sense if the idea if the integral of a function of one variable is equal to its average value, the average value of the function multiplied by the length of the interval. It's one of those things that is fundamental understanding of calculus, telling you that almost nobody comes out of calculus knowing. But we got to, we're going to reinforce that here with a more general idea. Okay, so I've now written out this interval. The integral. So you can see what the integral is. Integrating this function, now a different function. And we're integrating first with respect to y, letting y go from 2 to 3. And then we integrate with respect to x as x goes from 1 to 4. What does that mean? Now, right now, we don't have a real specific understanding of that meaning. But intuitively, if y goes from 2 to 3, and x goes from 1 to 4, and that's plausible because your y integral has limits from 2 to 3. I can go from 2 to 3. So, and x from 1 to 4. So what region of the plane does that correspond to? Well, I asked everybody to take just a minute and sketch that. Okay. Now, people are a little bit slow on this, but that's all right. We're seeing this for the first time, but I think everybody's got the right instinct. Okay, x goes from 1 to 4. So here I'm going to draw line x equals 1, and then a line for x equals 4. Then I'm going to draw a line for y equals 2, a line for y equals 4. If I want to. You might not want to shade it because there might be something we want to annotate inside the region, but it's such a simple region, we can draw it again if we need to. So I'm going to go ahead and shade it. Fair enough? Okay, so what we're talking about is this interval. Now, we could estimate this interval. Okay. We could divide this rectangle up. Let's assume this is the same rectangle. We could divide this rectangle up into a bunch of smaller rectangles, right? And evaluate the rectangle, put a number in each one of these if it corresponds to the value of this function. Okay. And now we might want to use the point at the midpoint of each interval. That would be convenient. But we could do like we do with the Riemann sum and just take any sample point within the interval, take a random point within each of the small squares, which in each of the small area increments, which is what I'm calling. Okay. And multiply the value in each of these area increments by the area. Okay. So we could sum up I'll say we'll sum up area times sample value for each small area increment. How many do I have here? 1, 2, 3, 2 area increments there. If I counted right, I'm not sure I did. Okay. If I did that, I would probably get a pretty accurate estimate of this interval. That makes sense? Now, when I did this, each of these increments had area 1. So when I summed these up, I got some kind of an estimate of total interval because the area is 1. If I multiply value by area and add them up, I get like 125. Okay. Whereas when I did the integral, I got 78, but I was being pretty careless. I'm not sure either of these is correct, but you could do it very easily. Okay. You could validate my steps very easily. I would have thought they'd have been a little closer, but this thing gets a pretty drastic slope eventually. This concavity means that the estimates we make based on the midpoint are going to tend to be low. And I say that was a qualification, but not too sure. Okay. But do we understand this picture, this idea? We're adding up area times sample value. We take a dartboard, first dart that hits in the thing, that's where we evaluate the function. Somebody else takes a different dartboard from the distance where they can't really pick their landing spot within each increment and bias the thing. They're going to get something a little different, but it's probably going to be pretty close. Unless this function has some pretty wild values in it, and it won't. I have a y squared in the denominator, so I got to be careful not to let y get too close to zero, because then things get wild, don't they? Okay. Okay, well, I could do that. What I would get would be a more or less reasonable estimate of what I get when I do this integral. Well, the integral's not hard to do. My antiderivative, the antiderivative of xy with respect to y, x is a constant. Antiderivative of y is y squared over 2. So my antiderivative would be xy squared over 2. Okay? Makes sense? And my antiderivative here, well, that would be negative x over y. Now, just to be sure, because when you're integrating reciprocals, it's really easy to go the wrong way with your integral. So you want to take the derivative of this. What's the derivative of 1 over y? Well, it's negative 1 over y squared. Okay. Derivative of y to the negative 1 is 1, y to the negative 2. Okay. So you check that out so you don't do any bonehead thing like you often see me do. Okay. Especially when I don't check things out carefully. And then that's going to be evaluated for 3 and 2. And then whatever you get from this, you're going to integrate with respect to x. Okay. After you've done a couple examples, this is very easy. Assuming you don't have like the arctangent of e to the x squared over 5 or something like that, that you can't integrate anyway. Okay, I was kind of rudely interrupted by somebody who told me what the next 2 steps are going to be, and he's right. It was a polite interruption. It was a good question. And you're anticipating, and I don't see a lot of passivity in this group anyway. I don't think you get this far from passive. Okay. So anyhow, this equals the integral from 1 to 4 of what? Now, writing it out in more detail than I did in the first example, which I didn't expect you to necessarily understand in all its detail, although that was pretty simple because you had 2 separate variables. But here we have it. We just evaluate this for y equal 3, y equals 3, y equals 3, and then for y equals 2, y equals 2, and y equals 2. It looks like I got it right. Which I always think I did. You check in that. Okay. And then won't ask you to trust me on the arithmetic. But I think we're going to have 9 halves here minus 4 halves here, which is going to give us 5 halves x. And then it's negative x over 3 plus x over 2, which I think gives us x over 6. And again, don't trust me in that, tentatively trust me to verify it. So this equals what? Well, now you just have just plain old integral of one variable, right? And even better than that, it's linear. So I could actually combine these. I guess I probably ought to. 1 is 4, and common denominator 6, so it's going to be 15 minus 1, 14, 6, 7/3. Again, don't believe what I say automatically. Be a little bit skeptical. And now it's going to be just to be real explicit, 7/3 times x squared over 2 evaluated for 24 and 1, which is 7/6 times 15, 105 over 6, which is like 15, 16, 17, I think. Okay. Now, if we had made estimates, even if we break this thing into 1 unit squares and do sample points and sample the values of the function, or even if we could sample the value of the function in each of the 4 corners. Okay. What's the value of the function at this corner? Well, this corner is x equals 1, y equals 2. So you get 2 from this, and you get 1/4. So you get 2 1/4 here. At 1, 3, you would get 3 and 1/9. Now, again, I'm just evaluating the function at the corners to see if this result is plausible. If I evaluate at the point 4, 2, I get like 8, and I get about 10 here. Get like 16 and a fourth. If I average these numbers, we get about 26, 30, and if I average these numbers and divide by the area, well, first of all, if I average the 4 numbers, I get something like about 9. Multiply that by the area, which is 4, 3, I get like 27, whereas here I get 17.5. Okay. So the number's in the same general ballpark. Do you understand what I'm saying? I'm saying that this function, if you think of this graph of this function, it's 2 1/4 units high here. It's a little over 3 units high here. It's a little over 16 units high here, 10 units high here. Probably slopes down rather quickly. Okay. And from Well, I'm not gonna try to gesture it. So it's low for a while, but it gets kind of high here. If I average these four values, I don't get a real good estimate. It would be good to make an estimate like for the midpoint here, but I'm not gonna take the time to do that. And see how that compares with the estimates at the left and the right. It's a good idea to do some kind of numerical validation of these intervals. So you understand what the integral means. We're taking the value of the integral times the area. Region. Take the average value of the integral times the area of the region. So if the plane is here and the curve looks like this, then you figure, well, maybe the average value is about here. And if you multiply that by the area, you should get something reasonably close to what you get when you do the integral. Then that makes sense of the integral. It makes sense of what you're doing when you're integrating. So you might throw that away. But that's the process. That's the mechanics. I don't even guarantee I did every step of that right. That's okay. So the fractions and stuff I did once, I didn't think twice about it. Okay. Now it's not a big deal thing that you do. The same integral can be done in the opposite order. If you do it in the opposite order, the steps are going to look a little different. Now over here, when I wrote down this expression, I got one integrated with respect to y and evaluated it 3 and 2. As I did in the first example, it doesn't hurt to say y equals 2 to y equals 3, so you don't accidentally substitute what should be a y for an x. Does that make sense? In other words, you want to keep track of what it is that's going to be substituted here. Because you catch that x out of the corner of your eye and decide to, that kind of thing I do, and decide to just substitute these numbers for x. I've done a lot of these integrals, so I probably wouldn't actually do that, but that would be kind of thing that I would tend to do. You have your own tendencies to pick up the wrong thing and put it in the wrong place sometimes. So it's useful, especially when you're getting started, to write x equals 1 to x equals 4, because we're integrating with respect to x, we want to substitute for x. If we do that, we have the integral from 2 to 3 of, so that's going to be 16y, but then it's going to be minus 1y, so that's going to be 15y. And you can do the details to understand what I'm doing here, but that's going to be 16 minus 1. And I think if I did that correctly, it might be. Okay. And then I integrate with respect to y. So I get 15 halves y squared minus 1 over y. Y equals 2 to y equals 3. Okay, now 3 squared minus 2 squared is 5. So I get 75 halves. I'm already in trouble because I'm getting something way bigger than what I have there. And then minus 1 over y. That's going to be minus 1/3 plus 1/2, which will be plus 0.16. And that does end up equaling what I had over there, so I had a mistake somewhere. So that's gonna be like 37 2/3. Doesn't agree with what I got there, but it should. Now I combined a lot of steps in my head. Oh, I see one problem already. Not gonna make much difference though. Actually, maybe it's gonna make a difference. It'll make it even worse. Could have been 15 over 1 squared here. It turns out that I think that's before. Okay, so I did something wrong, but do the integral yourself, see what I did wrong. If you do these integrals correctly, they're gonna come out same value. The value is gonna be fairly consistent with what you get if you did some numerical approximations. And what I'm demonstrating here um the idea. Um Now let me take a quick look at the problem set again. See what else I might want to tell you. Okay, on the homework, you're gonna do things by approximation. And then you have some integrals, they say integrate by reversing the order of integration. And sometimes it's a big advantage to reverse the order of integration. A lot of times it doesn't matter, like for these functions, it didn't matter much. When you reverse the order of integration, let me just caution you, if you're integrating with respect to y, your limits are the y limits. So that when you reverse the order, you make sure that the y limits that were 2 and 3 here are 2 and 3 here. The y limits go here. The x limits are 1 and 4, and those are the x limits on this interval. Okay, that makes sense? You just got to keep y with y and x with x. And then remember to treat x as a constant when you're integrating with respect to y, and y constant when you integrate with respect to x. And it can be an advantage if you then check your antiderivative by doing the appropriate partial derivative to see if you get back to where you started. Okay? Okay, let me do this example now to show you the importance of the potential usefulness of reversing the order of integration. If I integrate this, I enter integral I sine x sine y evaluated from x equals 0 to x equals pi over 2, and then integrate that with respect to y. Okay, well, the sine of 0 is 0, sine of pi over 2 is 1. So the sine of x is going to go from 1 to it was going to have values 1 and 0. And that's just going to give me the integral of y with respect to y, which is then going to be negative cosine of y evaluated at 0 and pi equals, or said cosine of pi is negative 1, so you're going to get a 1. Sine of 0 is 1, you're going to get minus a negative 1. That's equal to 2. All right, reverse the order of integration. I didn't reverse my variables there. How my limits 0 to pi are with respect to y, and now they are. And my limits 0 and pi over 2 are with respect to x. M for x goes 0 to pi over 2. Okay, so now I integrate with respect to y, I get negative cosine x cosine y evaluated between 0 and y. Then with respect to x, integral 0 to pi over 2, then of what? Okay. Again, if x is pi, cosine of x is negative 1, and the negative of that is 1. And we're going to end up with 2 cosine y. Cosine x dx. And if you complete the integral, your antiderivative is going to be the sine, and you're going to get 2 times the sine of pi over 2 minus sine of 0, which is going to be 2 again. Okay? Make sense? Just another example of reversing the order of integration with fewer numbers and fractions to deal with so I could get it right. Okay. So in many cases, the order of integration doesn't matter, but in some of the problems I chose, I think it will. I think it'll be easier to integrate in one order than in the other, and that often happens. And you want to start to develop an awareness that that can be the case, because sometimes you can save yourself a huge headache by integrating in a certain order. Okay. Okay. Let me take another quick look at the problem sets.